to the video on volumes of revolution. So basically what we're going to start off with is a graph. Okay, so let's say we have an x and a y, and here's our function f of x. Okay, so let's say we have this function, and what we're going to do is take an interval from a to b. Okay, so we're going to take this chunk right here, we're going to take this graph, so this area here, and what we're going to do is rotate it about the x-axis. Okay, so we're going to take this whole chunk, this piece right here that I'm outlining, and what we're going to do is rotate it around, like we're kind of spinning it toward us and then away and then toward and away. Okay, so it's kind of just spinning around here. So what that means is that at each point, so let's say we have our value, let's say we're at point A here, and so if we go up and touch our graph, now we're at f of A, right? That's the value. So this is f of A, that's our height, which is actually going to be the radius of our circle. Okay, so f of A is the radius, equals the radius of our circle, of the circle at x equals A. Okay, so when we do that, then we get a circle that looks something like this. Okay, and this is only for the point A. Alright, so let's say if we did the same thing for B, then if we go up, this is going to be at the level f of B, so that'll be our radius at B. So f of B is the radius of our circle, radius of the circle at x is equal to b. And this one's going to look like another circle, like this, okay? And then we're going to do the same exact thing for all of the other points within. So then we're going to get some kind of solid that looks like this, okay? So it's going to look a little bit like such, alright? So what we're going to get is this big volume here, and the formula for that is the following. So since we're going to take all of these points, such as A and B, we pick the endpoints here, and we make those circles. So what we're going to do is take the area of the circle at x equals A, okay, and that is equal to pi r squared, right? Pi times radius squared, which in this case was pi times f of A squared, right? Because that was our radius of our circle, the height or the value of the function. And then we're going to go all the way down. We're going to calculate at all of the points in between A and B. So that's what the dot dot dots mean. And then we're going to add up everything up to the area of the circle at x equals B. And then that's going to be our pi r squared. And in this case, that's pi times f of B squared. Okay? So we're going to take the area of all of these circles, and that is going to be in total the volume of this solid. Okay? So formulaically, that's going to look like, so we have volume of the solid is going to be equal to the sum of the areas of all, this is important, of all the circles ranging from A to B, x equals A to x equals B, A to B. Okay, so what this is going to look like is basically we take a general formula. So volume is going to be equal to the sum of, so whenever we're adding up a sum of infinite things, then we have the integral from A to B, okay, of pi r squared, because this is the area of a circle, the formula for the area of a circle, right? So we're going to add up the sum of all of these areas of the circle from x equals A to x equals B. And in this case, our r is equal to f of x. That's our function value, right? So our volume is actually going to equal the integral from A to B of pi times f of x squared dx. Okay? And that is the volume for our, or that's the formula for our volume of the solid. And we can always move this pi outside because that's just a constant, right? So we're going to get pi times then the integral from A to B of f of x squared and then dx. Okay? Alright, so let's do an example of this, computing the volume. So what we're going to do is compute the volume of the solid obtained or reached by rotating, because that's what we're doing. We're rotating or revolving a region, so the region under a curve. So under, in this case, we're going to do the parabola, so y equals x squared, about the x-axis, okay? And then we'll give an interval for 0 up to a positive 2, Okay, so our interval is 0 to 2, so that's our a. A is 0 and b is 2. Okay, our function is f of x is equal to an x squared. Alright, so now we're just going to plug this into our formula that we know for the volume of a solid. So that's going to be pi times the integral from a to b, with our f of x being squared and then dx. Okay, so this is going to be volume is equal to pi times the integral from a to b is now 0 up to 2. And then we're going to take our f of x, okay, x squared in this case, and we're going to square it and stick it in the interval, or into the integral. Alright, so here we're just going to compute. So we have integral from 0 to 2 of x to the 4th dx. Okay, so then this is going to turn out to be v is equal to pi times x to the 5th with a 1 over 5 in front, evaluated from 0 up to 2. Okay, so this is going to be a pi over 5 times x to the 5th from 0 to 2. So this is going to be pi over 5 times a 2 to the 5th minus pi over 5 times 0 to the 5th. Okay, so this is going to end up being just, let's see, what do we have here? So v is equal to a pi, a 32, because that's 2 to the 5th, pi over 5, and then this term goes away, it goes to 0. Okay, so that's going to be the answer to our volume problem. Alright, so from this process, or from this calculation of finding the volume of solid, there are a bunch of useful and kind of neat variations on that process. So here's one where we're going to rotate a region between two curves. Okay, so here it gets a little bit tricky, but like I said, it's just a variation on the same process. Okay, so let's draw a graph and see what we're working with. So let's say we have our x and our y. Okay, we have a graph, let's say f of x up here, and then another graph down here called g of x. Okay, and then here's our interval a to b. Alright, and we want to rotate not the entire region, but the region in between. So we want to rotate this, let's say, around the x-axis. Okay, so here we kind of have to reevaluate what we're looking at. Our radius isn't just one function or the other function. It's going to be some kind of combination of both. Okay, so let's look at the point A. What do we have going on? What is the area of our shape? Okay, so the upper, or the furthest radius is going to be to the f of x, right? This is our upper one, or the greater function. So this is going to be what I'm going to name capital R. Okay, and then if we start again at the x-axis, our axis of rotation, right? Then we're going to have that the lower, or the lesser radius is to our g of x. Okay, that's the shorter function here. Okay, it's the shorter as in like the closest to the x-axis, or to our axis of rotation. So that means when we rotate this around, what we're going to actually get, instead of a solid circle, so this is the solid circle we obtained by rotating f of x around, so our capital R, the bigger one, but then we don't want this, the area of the entire circle, we just want the area of this washer here, okay, because that means we don't want this area in there, okay, we really don't want that, we just want this top piece. So whatever's in between f of x and g of x, we want that to be rotated around. So the middle is, in a sense, going to have a hole in it, right? This whole thing is going to have like a tunnel through it. All right, so that means that we have to scoop out this inside circle, which is with a radius of g of x, which is the small r. Okay, so in a sense, we're going to have the large circle, so large circle minus the area of the small circle. Okay, so what this is pi capital R squared minus pi little r squared, right? That's the area of the large circle minus the area of the small circle. And in this case, our big R is equal to f of x, and little r is equal to our g of x. Okay, so this is going to turn out to be a pi times f of x squared minus pi times g of x squared. All right. So that's what we're going to do for each of these points, and we're going to integrate this, basically, from A all the way to B. Okay, so we're going to get some kind of solid that looks kind of monstrous, right? But it's going to have this hole through the middle the whole way. Okay, the whole way. No pun intended. Anyways, so yeah, it's going to look something like a cylinder with a chunk cut out of it. So again, we're just going to take this formula down here, and we're going to integrate it from A to B. Okay, and that is basically going to be our volume. All right. So I'll write it on the next slide. So when we rotate a region between two curves, so rotating a region between two curves, between two curves, then we're going to have that our formula is equal to v is equal to a pi times the integral from a to b of f of x squared minus g of x squared. Okay? And this is, or I guess a more general way of writing this is that we have v is equal to pi times from a to b, the furthest one, so I'm going to say capital R squared minus little r squared dx, where r, capital R, is the furthest function away from your axis of rotation, furthest from axis of rotation, which in the last case was our just the x-axis, right? So y equals 0. So that didn't really make a difference, but then we'll see later on how our axis of rotation can change. Anyways, and then our lowercase r is the closest to our axis of rotation. Axis of rotation. Okay? So now, actually, we're going to see where can our axis of rotation be. So, if you don't